In this video, we'll be learning how to predict the molecular geometry of molecules. Molecular geometry refers to how atoms in a molecule are arranged in 3D space. To do this, we'll be using VSEPR theory, which is spelled VSEPR. And VSEPR stands for valence shell electron pair repulsion theory. When two atoms bond, only their valence or outer shells make contact. Covalent bonds involve a pair of electrons being shared between two atoms, and because electrons repel each other, since like charges repel, this causes the atoms in a molecule to orient themselves accordingly, which gives molecules their geometry. This is where we get VSEPR theory from. Typically, electron pairs in a molecule want to stay as far away from each other as possible. So they will assume a configuration that maximizes the distances between each other. When it comes to electron pairs, there are two types we will consider: bonding pairs and lone pairs. Bonding pairs are electron pairs involved in bonding, such as single bonds, double bonds, and triple bonds. And lone pairs are electron pairs not involved in bonding. For example, for bonding pairs, we treat double and triple bonds as single bonds in VSEPR theory. For example, even though a triple bond has 3 electron pairs shared between the two atoms, we will treat it like a single bond with only 1 electron pair. Why is this? Double bonds include 1 sigma bond and 1 pi bond, and triple bonds include 1 sigma bond and 2 pi bonds. So we only count the sigma bonds in double and triple bonds, not the pi bonds. Since they only have 1 sigma bond each, we count 1 electron pair for double and triple bonds. With that being said, let's try to understand molecular geometry using molecules with very simple formulas in the form of A, B sub x, where A and B are 2 different elements, and the central atom, the A, has no lone pairs surrounding it. The subscript x is just a number, such as 2, 3, 4, etc. And we'll only be considering molecules where the subscript x is between 2 to 4. So let's take a molecule that has a chemical formula of AB2. So in this case, it's going to be a molecule with 2 elements, and the second element, B, has 2 atoms in the molecule. So that is 1 central atom, letter A, and 2 atoms of another element surrounding it. For example, it could be a molecule like beryllium chloride, or it can be a molecule such as mercury chloride, HgCl2. So these are just examples of a certain type of molecule we want to examine. So now let's try and draw the Lewis structure of this type of molecule to understand what's going on a little bit better. If you remember, the Lewis structure tells us the bonding scheme of a molecule, not the geometry. So let's look at beryllium chloride as an example. So let's take beryllium chloride, and then let's draw the Lewis structure. So for beryllium chloride, beryllium is in group 2, and so it'll have 2 valence electrons. And chlorine is in group 7, so chlorine will have 7 valence electrons surrounding it. So we have to account for a total of 16 electrons, because 7 plus 7 plus 2 equals 16, right? 7 for each of the 2 chlorine atoms and 2 for the beryllium atom. And so we start with the central atom, in this case beryllium. We draw the 2 valence electrons next to it, and then we connect the 2 chlorine atoms to the beryllium atom so that they form covalent bonds. So in this case, we take one of our chlorines, we attach it to the beryllium atom. So we have chlorine on this side. Then we take another chlorine, or the other chlorine, and then we attach it to this side. So now we have the Lewis structure of our molecule, beryllium chloride. And if you want to draw the covalent bonds using bond lines, we can sort of redraw it like so. So we take any covalent bond and then we replace it with a bond line. Right? So either one of these two diagrams is appropriate. So to determine the molecular geometry of beryllium chloride, we want to determine the number of electron pairs around the central atom, which in this case is the beryllium atom, not the chlorines. So since there are 2 single covalent bonds around the beryllium atom, right, 1 electron pair here on the left and 1 electron pair here on the right of the beryllium atom. So since there are 2 single covalent bonds around the beryllium atom, there are a total of 2 electron pairs. And these are going to be bonding pairs because each of these 2 electrons, right, each of these electron pairs are involved in a bond. So that's why they're going to be bonding pairs. And so if you remember, the electron pairs repel each other and want to stay as far away from each other as possible, and therefore want to maximize the distance between them. So if we think of beryllium chloride as the heads of a clock, right, or the hands of a clock, right? So if we take the central atom, the beryllium, as the sort of the axis of the 2 hands, and then we draw 2 hands of a clock, right, the long hand and the short hand. So let's say the center is beryllium. This head of this hand is going to be chlorine, and this head of the other hand is going to be chlorine as well. So the position where there is 180 degrees between the hands is the position of the hands that maximizes the distance between them, right? So we want an angle between the hands of 180 degrees, right? This maximizes the distance between the bonding pairs between each chlorine atom and the beryllium atom. And so the molecule will assume a linear geometry because the atoms are arranged in a straight line. And atoms with a linear geometry are going to be sp hybridized. So that's going to be the way you find the molecular geometry of a molecule with the form of AB2 or AB sub 2. Now let's look at a molecule with the formula AB sub 3. So let's take a molecule with the form AB sub 3. AB subscript 3. And a molecule that has this form, for example, would be boron tetrafluoride. So BF3, boron tetrafluoride. And if we draw the Lewis structure of boron tetrafluoride, we have one boron atom, right, which is in group 3. So there's going to be 3 valence electrons. And then we have 3 fluorines, which is in group 7. So we have 7 valence electrons, right? So if we do the math, right, and we tally up all the electrons, all the valence electrons, we have 3 plus 3 times 7, which gives us a total of 24 valence electrons to account for. Right, so starting with the central atom, boron, right? The central atom is always going to be the atom with the letter A, right? Which in this case is boron. So we take our central atom, boron. We have boron, and there's going to be 3 valence electrons surrounding it, and basically we want to connect the 3 fluorines to the 3 valence electrons around the boron atom. So we take one of our fluorines, we connect it to one of the valence electrons, take another fluorine, connect it to another one of the boron valence electrons, and then we take the last fluorine and connect it to the very last valence electron, like so. So now we have the Lewis structure of boron tetrafluoride. We can sort of redraw this using bond lines, like so. We have our boron in the center, and then we have one fluorine, another fluorine, and our last fluorine. So but if you remember, the bonding pairs want to be as far away from each other as possible. Um, so right now, each of these bonding pairs around the boron atom, 1, 2, 3, are at 90-degree angles with each other. And so, but this does not maximize the distance between them, right? All three of these bonding pairs around the boron atom, 1, 2, 3, they want to be as far away from each other as possible. So they want to arrange themselves or orient themselves in a way so that the space between them is maximized. So therefore, these three bonding pairs will arrange themselves so that there are 120-degree angles between them, right? So it'll look something more like this in reality. So we have one bonding pair up here, and we have another bonding pair at 120-degree angle. And then we have another bonding pair at a 120-degree angle with the other bonding pairs. So, and in between each of these bonds, there is 120 degrees, right? And so this is sort of the molecular geometry of boron tetrafluoride, and so we call the molecular geometry for these types of molecules trigonoplanar, because the three fluorines from the corners form the corners of an equilateral triangle around the central atom, boron, and all the atoms lie on a single plane. And so, in this case, the central atom of boron tetrafluoride is going to be sp2 hybridized. Right, so that's going to be how to find the molecular geometry of molecules that take the form of AB3. So now let's look at molecules that take the form of AB4. So now we're doing molecules that have the form of AB4. And an example of a molecule like this is methane, which is CH4. Right? The carbon is the central atom, and it's going to be surrounded by 4 hydrogen atoms. So since there are 4 hydrogen atoms and 1 carbon atom in methane, we have to account for a total of 8 valence electrons. Right? Since carbon is in group 4, right, it's going to have 4 valence electrons. And since there are 4 hydrogens surrounding the 1 carbon atom, there's going to be a total of 1 valence electron for each hydrogen atom for a total of 4 valence electrons. So therefore we have to account for a total of 8 in our Lewis structure. Since right, so starting with the carbon atom, we draw the carbon atom with 4 electrons around it, right? 1, 2, 3, 4, 1 on each side, and then we connect the hydrogen atoms to each valence electron on the carbon atom. So we have 1 up here, 1 on the right, 1 down here, and then 1 over here. And then we can kind of redraw this using our bond lines, like so. And then 1 over here. So now we have the bonding scheme for methane, right? But what we're actually looking for in this case is the molecular geometry, right? So, since there are four covalent bonds around the central atom, uh, there are therefore four bonding electron pairs, and thus four electron pairs in total. And these pairs of electrons want to be as far away from each other as possible, like we discussed previously. So, in order to maximize the distance between each electron pair, the bonding pairs arrange themselves in a way such that instead of there being 90 degree angles between them, there are 109.5 degree angles between them, and therefore they form a tetrahedron. So if we were to redraw our molecule in 3D space with the correct angles between them, it will look something close to this. And so between each of these bonds, there's going to be 109.5 degrees. And then we call this shape a tetrahedron, right? And a tetrahedron sort of looks like this. So something like this, a tetrahedron. And um, in our molecule diagram over here, the dashed line represents bonds behind the plane of the page, or in this case the screen, and the bold lines represent bonds above the plane of the page or the screen. So four triangles form the faces of the tetrahedron, and each hydrogen atom forms its corners, right? And so we say that methane has a tetrahedral molecular geometry. Tetrahedral molecular geometry, and the central atom, in this case the carbon atom, is going to be sp3 hybridized. And so with that being said, thank you for watching and have a great day.